So the objective of our lecture today is to talk about some new additional features in Adams. We'll talk about some additional features in the creation of a body. We'll talk about points and markers and what are they. We'll talk about how can we build graphics for the ground, and then we are going to build the contact force between the projectile body and the ground. During this process, we are going to learn how to pick solid using mouse or from the model database. Also, we are going to look at how can we send a measure to the extended plot. The last thing that we will do, we are going to talk a little bit more about the plotting and post-processing in Adams. What we will do now is actually we are going to open an existing model, and we are going to import the model from the CMD file. So I will start from an existing model like this, and then we get this open existing model window. In that window, in the first line here, you see what is the file name. So we are going to browse to where we saved our file. So I will click on this icon. It will take me with the Windows Explorer. So I'm going to browse to where I saved my model. This is my model here. And now I'm going to import this CMD file. So I will click on projectile.cmd. I will click open. So when we open our model, make sure you have this checkbox checked so that this will be our working directory. Whatever files we are going to create today will be saved in this directory. So now we have the model. I am going to leave the defaults and I'm going to click OK. Once we click OK, as you can see, Adams imported the model. Adams created a graphics strip for our measure. We have the projectile is right here, and we have, if you look under the bodies, you will see the projectile body. We have the sphere, and we have the markers associated with this body. If you look at the ground doesn't have anything in it. Also, if you look under forces, you will see we have the gravitational force only. I'm going to change the screen background so you can see it better. So this is our screen background. Now, in order to check if the model is working, I'm going to run the interactive simulation. So we'll go to the simulation tab, select the interactive simulation tool, and over here you can see the end time. In this case is 1 second. Number of steps is 50. For this simulation, I would like to define the step size, not the number of steps. So what I'm going to do, so I'm going to change the number of steps. Instead of 50, I'm going to change this to time step or step size. So in the step size, I'm going to use the step size 0.01, and as you remember, this will be the step size for the integrator. In order to solve the mathematical equation, the integrator is going to consider this step size. Now, if I run this simulation, I will expect this body to fly and then fall down. This strip is going to define the y displacement of our projectile. So if I run the simulation, Msc Adams is generating the equations, and now it is solving the equations. As you can see, the projectile is flying. While the projectile is flying, the measure is updating the graphics. Now you don't see the projectile within the screen because our graphics was not zoomed out. So I can zoom out a little bit in order to see the motion of our projectile. In order to zoom out, to remind you, we have the keyboard on the screen, the keyboard Z. You can click on the keyboard Z, and this will allow you to zoom out like this. You can drag the mouse to zoom in and out. Also, you can translate the object or the working grid over by using this hand or using the key T for translation. So on the keyboard you can hit the T, and then you can drag your model like this. Now if you run this simulation again, you can see the model is flying, the projectile is flying, and also still going out of the screen. Okay, now let me tell you something here. As you can see, while Adams is solving the equations, Adams is updating the graphics. And you can see the progress of the simulation down in the status bar right here. While we are building the program, the model, or we are debugging the model, this will be a nice feature that we look at how the system is behaving. However, updating the graphics takes computational time from Adams and make our simulation slower. So what we usually do, once we are confident our model is complete and our model is correct, and we would like to run an actual simulation, we don't want to update the graphics. What we want is to have efficient computational time. In order to improve the efficiency of the computation, we ask Adams to do the simulation only, solve the equations only, and later on we can look at the results. This checkbox right here, update graphics display, when this box is checked, Adams is going to draw the system while it is simulating. If we uncheck this box, what is going to happen? Adams is going to solve all the equations and store the results without updating the graphics. And this will have significant effect on the simulation time. You can notice this if we run the simulation. Notice how long will it take. So if I'm going to run it, done. While if you have the graphics, you can notice how long will it take. Oh, I have to reset to the original configuration, so I'm going to reset it here. Run. Still working. So now you can see the difference between updating the graphics and without updating the graphics. So most of the time we use this feature while we are building the model or debugging the model. When we run an actual simulation, we don't update this graphics. So what do? We need to look at the motion of our mechanism. You can either use this film strip to open your animation window, or go to the results and use this strip here to open the animation window. And this will allow you to have good control on the animation. You can animate it any way you want. So now what Adams is doing, it's just reading the results and updating the graphics to generate this animation. So now assume we have this measure and we have created a good measure, and we would like to have this measure in the extended plot so we can have more control in the measure and display the graphics in a way that we can send it to other reports. If you would like to send a measure to the extended plot, you can right click, you can first highlight the measure and then choose right click. As you can see, this menu contains the first element, says transfer to full plot. So transfer to full, if we choose transfer to full plot, it's going to open the Adams post-processing window like this, and it will generate a plot for our measure. So now, as you can see, the plot is created, and as you can see, this is actually taking the results from the last run. Now, if you would like to have control on the plot, you can go to the graphics plot. This is our page. You can change the page name. I'm going to call this measure. And then you have the plot. As you can see, this plot has only one curve, this curve right here. This curve represents the y displacement from our projectile motion. You can give it a title if you wish. So now the title is y displacement, which is the measure name. The x-axis is the time. The y-axis is the displacement in the y direction. So we can change the y-axis name. We can call it attitude. So I'm going to call this, instead of being vertical length, this will be the altitude. So you can change the name. Instead of length, we go to label and make this altitude. If you would like to add more graphics into this window, you can do that. If you want, you can do that. Or if you would like to add the x displacement, y displacement, you can create a new page from here, and from this new page you can add the new plots that you have. What I'm going to do now, I'm going to add the ground and create contact with the ground. Before we do this, I'm going to save my model with a new name. So I will click on, if you click on save, it will save it with the same name, projectile 1. But I would like to create a new database. So I'm going to go to file and select, from file I'm going to select save database as. Instead of projectile 1, I'm going to call this projectile with contact. So this will have a different name for our model for the future reference. I will click OK, and you can see this model have been saved in our database right here. So now let's talk a little bit about the geometries in Adams. As you know, when we create geometries, we usually would like to use reference points. So Adams allows you to define a reference point, and the reference point is defined with respect to the global coordinate system. So if we assume this is our global coordinate system with the origin right here, this is our origin, this is coordinate x-axis, this is y-axis, and this is z-axis. If you would like to create a point, say point B, you will need to define the position vector of this point. This position vector can be defined with respect to the global coordinate system. How do we define the position vector? As you can see, the position vector can be defined by the coordinates in x, y, and z. So here this will be the coordinate in the BZ, RB in the z direction. This will be RB in the y direction, and this will be RB in the x direction. So if I would like to define a point, I usually define the coordinates of this point in the x, y, and the z direction. So I need to define the x coordinate, the y coordinate, and the z coordinate in order to define this point. Another very important feature in Adam is with what we call it a coordinate system or marker. The term marker in Adams refers to a coordinate system. The coordinate system usually is something like this. It's a set of 3 axes three perpendicular axes. So you can have the x-axis, y-axis, and the z-axis. So I can call this x bar, y bar, and the z bar. As you remember from the kinematics, the coordinate system is defined by an origin and orientation. The origin is defined by its position with respect to the global coordinate system or to a reference system. So I can call this R marker. So in order to define this position vector, I need also the coordinates in x, y, and z that will define the origin of this marker. Also, because the marker can be oriented with respect to the global coordinate system or with respect to the reference system, I need to define the orientation. So for the marker, I need to define the marker coordinates, the origin of the marker, Rx, Ry, and Rz. And also I would like to define, I will need to define the angle, the rotational angle with respect to x, with respect to y, and with respect to z. If I define the position of the origin of the marker and the orientation of the marker, I can define this marker with respect to the reference coordinate system. In general, by default, if we don't define the orientation angles, Adams is going to consider them parallel to the reference coordinate system. But there is another feature that Adams allows you to do. Adams allows you to refer something relative to something else. For example, assume I defined this marker. Let's call this marker 1. So I will have O1, X1, Y1, and Z1. Now there is another marker that I know its position. I know the marker, the new marker position with respect to this marker. So assume the marker is right here. This marker has origin O2 and it has the x-axis, y-axis, and the z-axis like this. But this new marker is like this, is not defined parallel to the origin, it's defined like this. This new marker I know its position with respect to marker 1. So I can say the position of RO2 with respect to RO1. And I know this marker with respect to this marker have been rotated around the z-axis. If you notice, if I rotate this marker by 90 degrees around the z-axis, what is going to happen? The z will point down and the y will point in this direction. So actually this new marker right here resulted from translation from O1 to this position O2 along this position vector RO2 with respect to O1, and then it has been rotated by an angle 90 degrees around Z1. When it is rotated, X pointed down, Y pointed to the right, and Z remained in this position. Now this marker, I have the option to define it with respect to the global reference coordinate system or with respect to this coordinate system. When it will be easy for us to do something like this, if we have a marker on a body, it will be much easier for us to define the marker with respect to a marker on the body. If we have a marker on the ground, it will be much easier for us to refer to the global coordinate system. So I can define a marker with respect to the ground or with respect to the global coordinate system, or I can define the marker with respect to another marker. And this is very nice and important feature that we use in Adams. So now we learned that we have point. This point can be defined with respect to a reference coordinate system. This point also can be defined with respect to a different marker. It doesn't have to be all the time with respect to the global coordinate system. I can define a point with respect to a marker. The marker is defined by its origin and orientation with respect to a reference coordinate system. The reference coordinate system could be the global coordinate system, or it could be another marker on a body or on the same body. So how this can help us in generating our graphics? The graphics in Adams are defined by markers. For example, we learned how to create a sphere, and in order to create the sphere we need to know two important parameters. Where is the center of the sphere and what is the radius of the sphere? Those two important parameters, we can use them to define the sphere. Once we define those parameters, the sphere can be created. So how do we define the center of the sphere? We can define the center of the sphere by a marker. So I can say the center is located at this marker, the origin of this marker, or at point. Other geometries would require more than only the center and the sphere. For example, let's talk about the sphere first. The sphere would need the center C and the radius R. So the marker at the C and the radius R. What if we have a cylinder? How do we define a cylinder? The cylinder is defined by two things. The cylinder typically has a center line like this. This center line will pass through the circle, the base circle like this, and then you can extend your cylinder in certain direction. This is going to be a dotted line because this will be the hidden line. So we can use this dotted line here. As you can see, the cylinder would require more information. The first information that we need to define is where is the center of the base. So this marker here, we can say this is the center of the base. Marker, center of the base. And also would like to know what is the radius of your circle, of your base circle. So R is the cylinder base circle radius. What else? We need also the length of the cylinder. So this height, we need to know how much is the height of our cylinder. Now, very important parameter for defining the cylinder is the direction. Where is the axis of this cylinder is going to be? As you can see, the axis of the cylinder is perpendicular to the base. So the marker that we use to define the base, this marker is going to define the direction of our cylinder. Another very important geometry that we are going to deal with is box. So if you remember, the box is basically this. It has this rectangle, So assume a box like this. The box, as you can see, it has 3 dimensions. This dimension here, this dimension, and this length. Now, how do we define the box? Usually the box is defined by this corner. So we attach a marker to this corner like this. This will be the base of creating our box. So this will be the origin of the marker, will define the beginning of our box. And from this box we can define the 3 dimensions. So we can have the base, the length, and the height, depth. Those 3 dimensions will define this point. So if I define the dimension B, I can extend into this direction until this point. And then the length I can extend from this dimension to this point. And then the height I can extend up until I reach this point. So the origin marker define the left bottom corner, and the dimensions define this opposite corner. And this is how we define the geometry for a box in Adams. Other geometries, we can talk about them as we need in the future. Now, if I would like to create a box for our projectile, or we define a ground for our projectile, we are going to use a box. In order to create this box, we are going to need the position of our marker, and we are going to need the dimensions of our ground. And this is what we will do in the next step. So let's go back to Adams and create this box. I have this box, right, this our model here. I'm going to center it. So I'm going to take the model like this. Now I would like to create the box. I'm going to position the box below the sphere, below and behind. So maybe this will be a good point that we can create our box. So how to create a box? I can go back to bodies and select this box. Now remember, this box is going to be attached to the ground. This graphics that will be representing the ground that our projectile is going to hit. So because we are going to attach it to the ground or add this geometry to the ground, I don't need to add a new part. So I'm going to select from this drop down menu, I'm going to select add to ground or on ground. If you select add to part, you can add it to either the ground or to any other part in the system. But I'm going to select on ground such that it will be attached to the ground all the time. Now, as you can see here, you can define the length, height, and the depth of your box. So I'm going to make the length a little bit big. So I'm going to check this box and make this length. This is going to make this length 3 meters. 3 meters will be equivalent to 300 centimeters. The height by default is defined as 20 centimeters. I'm going to make it only 2 centimeters. We don't need too much height. And the depth, we are going to leave it as 20. So I'm going to check this box. So these are the dimensions that we just talked about. The dimension, the length, depth, and the height. Now, once you move your cursor on the, you can see the geometry is moving with you along on the Adams window environment. And as you can see also, when you move your cursor, the point is jumping. The geometry is jumping from one grid point to another. So from here to here, it will jump from here. And notice also, only the this bottom corner is jumping, because this is the marker that defines this corner right here. So now, in order to attach, to position this, I can right click anywhere you want, or you can actually bring out the event location by right clicking. So I'm going to right click and define the location event. As you can see, it is defined as 200 minus 200 minus 200 and 0. I'm going to allow you to do this. I'm going just to select apply. Once we select apply, Adams positioned the graphics for us. Oh, we don't see the graphics. Where it is?
It's right.
It's white.
Yes, it's right.
Yes, it's white, Doctor.
Because the graphics is
We need to
white.
change the background.
Because our background color is white and the box geometry is also white, we cannot really see it. But as you can see, we have a marker created. This marker is created where we positioned. And also you can see underground, the ground body now has this sign. If I expand this sign, you will see the two things. You see number one is marker named marker 3 and the box named box 8. This marker 3 is the marker that is used to define the lower left corner of our box, this one right here. And also you can see the box. Once you click on the box, you don't see it. So now this may be a good time that we can change the color of an object. How can we change the color of an object? If I right click on this box, you see something called appearance. So what is appearance? If you click on the appearance, it will show you different options that can control the appearance of this body. You can turn the visibility on and off, so you can show the body or hide it. You can show the name of the body or hide it, and you can select a color. Right now there is no color specified, but you can specify your own color. So how do I specify a color? You can type the name of the color, or you can right click over here. You will get this nice selection window. So now color says you can either browse or guess. I usually use guess and select one of those colors. For this nice ground, I'm going to select green. Now if you click apply, you can see the color of our ground change it to green. If you would like to see this in a shaded form, you can go to this icon right here, toggle between shaded and wired. So you can toggle between shaded and wired. I don't know where this warning is coming from. Okay, so now as you can see, our box have been created and the color have been changed. So I'm going to click OK. Now I exit from this. Usually we give every object a name such that we can refer to this name when we need to use it. This box we are going to call this the ground box. Instead of only just box, we are going to call it ground box. So this will be ground box. How did I change the name? I can right click and choose rename. So it will give me this box, gives a new name right here, ground underscore box. Or I can click and click again and then type the name. Once I finish typing the name, I hit enter. So I renamed the geometry to become a ground box. Also, it will be useful if we define this marker, give it a name. So we'll call this marker 3. I'm going to change it to marker corner. I'm sorry, box, ground box corner. Again, how do I change it? Using either of those systems. So I'm going to click again, and then I'm going to call this ground box, G box, corner. So now I know this marker is representing the corner of our box. Now this looks nice. For now, we can continue doing our simulation and see what is going to happen. But before this, let's look at how this looks in 3D. I'm going to close this measure. I don't need it for now. Let's look at this geometry in 3D. If I click on this isometric view, it will show our model like this. But notice something here. If you look at the sphere is coincident with the edge of our box. Okay, if you look from the top, it will show you exactly that the box is right in the middle of the sphere. So if we run this simulation and look at the contact between edge and sphere, is not going to look good. So it will be nice if we move this box such that the sphere will be in the middle. So what we are going to do, we are going to shift this box backward in the Z. How do we do this? We can change the marker. We can change the position of this marker. So in order to do that, I'm going to look at the isometric view again. I'm going to change this marker right here. So how do I change the marker? You can right click on the marker from the tree, right click on the marker and select modify. Or you can select the marker from the window right here and then right click and select modify. But see, when you select it from the graphics right here and right click, Adams is going to give you all the objects in this area. Do you want to select the ground part? Do you want to select the block, the box for the ground? Or do you want to select the marker? I need to select the marker. So this is going to be a little bit confusing. Instead of selecting from here, I can right click, go directly and select it from the tree. So I'm going to select the marker and right click on the marker and select modify. As you can see, this window, marker modify window, you can select the location of this marker. As you can see, the location of the marker at x coordinate minus 200, y coordinate minus 200, and the z coordinate is 0. So what I need to do actually is to push this marker in the negative z direction. So I need to change the coordinate in the z. I'm going to make it minus 100. So once I change this, it should move this marker in the negative z direction. Notice also what is the reference that you are using for this marker. As of now, Adams is using the origin of the projectile as the reference. You can select any other marker. For example, you can right click here and select the reference frame. See? You can select the reference frame any way you want. Now you can select, pick a marker to represent your reference frame, or go and browse database to select the reference for this marker, or you can look at suggestions from Adams. For now, I don't want to change the reference of this marker. I would like to refer it to the global coordinate system. So I'm going to leave it here. So now this position minus 200 x minus 200 y minus 100 in the z. Now let's see how this changes. If I moved it like this, how this will change the position. I'm going to click apply only. So now what happened when we clicked apply? It moved the marker for us. Now we can look from the top view. You can see the sphere is right in the middle of our box. And this is exactly what is needed. Before we leave this window, you can see also we can change the orientation of the marker. So now this orientation here, you can define the angles with respect to a certain marker. You can align a marker along axis orientation or in plane. Let me show you what is going to happen if we change those angles. First of all, it's going to rotate with respect to the global coordinate system. Now assume I'm going to rotate 90 degrees around the z-axis. What is going to happen? Let's make this 90. Click apply. See what happened? It rotated 90 degrees counterclockwise around the z-axis. So this is our box right now. I will put it back. So I'm going to make this 90 degrees, 0 again. So now you can see it here. You may also try, if you wish, you can try to rotate it around the other axis. 90 here. Oh, why did it rotate around the z-axis? This is the first angle, which is supposed to be around x. Why did it rotate around the z? This is what we call it the order of orientations, or the order of the angles in Adams. We will talk about it later on in details. But right now, we will put it back to 0 and click apply. So now I have our marker. The ground box corner is aligned with the global coordinate system, as you can see. Now I click OK. Now this is our projectile body. We have the ground. We need to run the simulation and see how this projectile is going to move. So what we will do, I will zoom out a little bit so we can see this projectile flying. Now I will go to the simulation, run the simulation and see how it's flying. I'm going to keep the update graphics so we can see what is happening. I will click on run, start simulation. So now it is flying. Oh, what happened? It looks like our ground box was short. So let's go from the side and see what happened. If I run it again. Oh, actually what happened is not short. Our ground is not short. But what happened? The ball went through the ground. If we run the animation to see what is happening, you can see right here. it's going through the ground. If you zoom on this part, if I would like to zoom in this part, what is happening? I'm going to select this tool, the rectangular zoom, and select the part like this. You can see the projectile or the sphere is inside the ground box. If you increment the frame, it's going through. If you go back, it's going through. If you look at isometric, you can see the ball is inside the box. So something is not right. Something is not correct. What is wrong? Remember, when we deal with those bodies, the Adams is going to deal with the bodies as pure graphics. Adams does not understand how to create contact between this body and this body. And in order to model the contact, this physical phenomena must be defined as physics inside Adams. So I must tell Adams that when this body comes close to this body, they are going to create contact and apply contact force when those two bodies come close to each other. How can I do this? We can do this by adding a contact force. So the next step is to create the contact force between this projectile body and the ground box. In order to add the contact force, we go to this forces tab, and then this special force says create a contact force. Click on it. Once you click on this part, you will get this window. Create contact, and this is the contact name. We can change the contact name, so we can call this sphere to ground, G box, ground box. And now you can see there is different types for the contact. If you click on this drop down menu, there is many options. We can talk about them later on, so I'm going to leave the default for now. I'm going to leave the default solid to solid. Now, in this box, we should define what are those solids. I solid is the first body, the first geometry, and J solid is the second geometry. And those two geometries need to be in two different bodies. In order to define the first body, I'm going to define the sphere. So I will click on this area and right click. Now Adams is asking us to select the contact solid. If you look at this, those options, you can pick the solid, browse the database and select it from the database, or you can look at the guesses. If you look at the guesses, Adams is going to give you some suggestions. I'm going to start with pick. Now, when I select the pick, Adams is expecting me to select a solid. And you can see this in the status bar right here. It says select a contact solid. So I'm going to select the sphere. Now, how do we select? You will move your cursor, and as you move your cursor on the screen, Adams is going to give you the name of the different geometries. So over here, it's showing the name of the ground box. Over here, it's showing the sphere for the projectile. Whenever you see the name of the object that you are looking for, click on it. So if I click here, it will appear as I solid. Now I'm going to repeat the same for the J solid. So click on this box, right click, and now I'm going to browse. You can pick also the same way we did, but I'm going to browse. If I select browse, Adams opened our database. So in our database we have two parts, the ground and the projectile. I need the ground, so I'm going to expand the ground from here. You can see now the geometry ground box, so I will select it from here and click OK. Now we selected the first geometry and the second geometry. Sometimes you can select multiple geometries to contact other geometry. For example, if I have multiple spheres that they are going to contact with this ground box, I can add more solids to contact with this body. We don't have multiple bodies right now, so we're going to leave those two selections here. Now, how do you want to model this contact? Modeling the contact or the type of the force between the two bodies can be modeled either impact, as you can see, impact force, or restitution force. So the impact, as you know, the impact will treat the contact between the bodies as if they are contact force, and damping, if you wish to add friction, you can do that. Or you can use the restitution, which is basically the difference, the ratio between the momentum before and after your impact. I'm going to leave for now the normal force using impact. This is the stiffness of the contact between the two bodies, and this is the damping. I'm going to leave the default values with no friction. Now I'm going to click OK. Once you click OK, you can see Adams created the contact force under forces and give it the name that we are looking for, sphere to ground box. Also notice this icon here. This icon represents the contact force for our model. Now at this point our physics is complete. I can run the simulation and see what will happen. So I'm going to click on simulation, run the interactive simulation using the same default values, because right now we are checking if this we would like to check if this model is working or not. We are going to leave the update graphics so we can see the motion of our projectile. Now I'm going to run the simulation. Adams is going to start creating the equation and solve the equations, and here it comes. So now you can see the projectile did not go through the ground. It fell from the ground. It hit the ground and then fall down. In order to have the simulation to run longer, we are going to extend the length of our ground and then extend the length of our simulation. In order to extend the length of the ground, I'm going to modify this geometry. How do I modify it? You can go under ground, select the ground box, right click and choose modify. If we click on modify, you can see the dimensions of our ground is here. You can see the name of the geometry. You can see the corner marker of this box, and this is the length of the dimensions of our box. I'm going to select this and make it say 6 meters. So instead of 3 meters, 300 centimeters, I'm going to change it to 6 meters. And click OK. Now you can see our box have been extended. So I'm going to zoom out a little bit. so you can see more contact. So now what we will do, we are going to run the simulation for 2 seconds and see what is happening. So I have the end time, I'm going to change this to 2 seconds. And then run. So you have the object hit the ground and then crawled on the ground. So what happened here, actually we didn't see any bouncing. We didn't see any bouncing of the ball over the ground. Let me repeat the simulation again. So it hits the ground and then roll over the ground. What happened here? What happened actually, because this contact model has damping in it, it will absorb most of the kinetic energy that we have. So in order to have more bouncing, I must reduce this damping a little bit. How can we do this? I can go to sphere, right click, and choose modify. I can change this damping. I can make it say 0.01. If I click on apply, it will apply these changes. Run the simulation again. So you can see some little damping here. So you can say from this simulation is not giving us what we are looking for. So how about if we change the impact force? Instead of impact, I'm going to use restitution. If we select the restitution, it will ask you for the restitution coefficient. As you remember, the restitution coefficient is an indicator for how much energy is lost during the impact. If we have the restitution coefficient is 1, it means there is no loss of the energy at all. But this is very ideal case and doesn't happen in our real life. So the restitution coefficient must be less than 1. For this experiment, I'm going to use restitution coefficient of 0.95. So what we did, we changed the normal force to restitution model. And then I'm going to change the restitution coefficient to 0.995. With the same contact force, all what I did, I just changed the physics that Adams is going to use to model this contact. So now I'm going to click apply. I will reset the simulation to the beginning and run the simulation again. The object is flying, hit the ground, and then bounce in the ground several times. Again, so you can run the simulation. You can see the first bounce is right here, and then it will bounce again, and then it will bounce back. Now I would like to see the path of our center of mass of the projectile. So I'm going to look at the animation, and I'm going to track the center of mass. So I will open the track marker, and then select the marker. So I'm going to right click here, marker, guesses. I don't see my body here. So I'm going to select browse the projectile center of mass and click OK. Now if I run this animation, you can see the center of mass of our projectile here. Notice also something, that the height, the altitude that the projectile have reached is decreasing every time. Also, you can see this from the measure. We had the y displacement measure. So I'm going to activate the measure from view. I'm going to look at the measure, open this measure in order to see the y displacement. As you can see here, very clear, the projectile does not reach the same height every time. So the first height, the first hit, the maximum altitude is almost 650. And then the maximum altitude is less than this. The second time, less than this. If I make the restitution coefficient higher, smaller, it means there will be more energy loss. So if I make this 0.9 instead of 9.5, I'm going to make this 0.9. I will click apply. Then I'm going to run the simulation again. So if I run the simulation, as you can see, it's taking longer because we are displaying the animation and also displaying the graphics for the marker. So the more graphics you display, the more time it will take to run the simulation. So now our simulation is complete, and as you can see, very clear that every time we hit the ground we lose some energy, and now the energies that we are losing are larger than the energies that we lost in the first time. Now assume you are interested actually in looking at the energy and how the energy is changing for your model. One way to do this is to look at the sum of the kinetic energy and the potential energy. We can do this in the post-processing. You can add a measure to monitor the energy, or we can go to the post-processing and look at the energy of the body. So let's go to the post-processing and study the energy that we will have. So I'm going to click on this plot, and I would like to generate a new plot. So I'm going to create a new page, this page right here. In this page, I would like to display the energy of our projectile, but I don't see it here. So I will go to the source and select objects. Now I can see the body right here. So I will filter by the bodies. Now I can see the object. I have only one body, which is the projectile, which is right here. Now if you look at the characteristics, you have the total translational kinetic energy, and sorry, you have the kinetic energy, and also you have the potential energy change. So if you look at the total kinetic energy and the potential energy change, we can plot them and see how they change. Let's first select the kinetic energy. So I'm going to click on this. The characteristic is the kinetic energy and the magnitude, and then select add curve. So as you can see here, this is our change in the kinetic energy. So once we select add curve, you see the kinetic energy. This is the magnitude of the kinetic energy of our body. Oh, so what is happening here? As you can see, we can interpret the change in the kinetic energy in terms of two things: the exchange of kinetic energy and the potential energy, and the loss due to the impact. So in order to look at also the change, those energies, I'm going to look at the potential energy. I'm going to add a new curve for the potential energy. How do I do this? In the same page, I can go to the layout here and select two side-by-side layout. So now if I select side-by-side layout, it should split this screen for me. The first one is what I used to plot the potential energy. The second one right here, this is the kinetic energy, and here I'm going to plot the potential energy. So I will select the potential energy from this characteristics, select the magnitude, and add curve. So as you can see here, this is the change in the potential energy. In order to make this clear, I'm going to move this legend down here. So I will click on this area, and here we have page number 2, plot number 3, this plot, and I'm going to select the legend right here, and I'm going to make it in the bottom left. Now I can try also with the same for this plot. I'm going to select the legend and bottom left, so I can see the changes right here. Now eventually what we should have is that the kinetic energy is going to change from the body is going to exchange energy between kinetic and potential energy. So the body started with this initial velocity, which will be certain amount of energy. The body started flying, so the body will start to go up. As the body is going up, the body is going to gain potential energy. And as the body goes up, the velocity of the body in the y direction is going to decrease. So as the body goes up, the velocity is decreasing and the kinetic energy is also decreasing. As you can see, the body will reach maximum height. At the maximum height, we have the maximum change or the maximum gain in the potential energy right here. As you can see, at the maximum height, actually there will be zero velocity in the y direction, but the body is still moving in the x direction. It has velocity in the x direction. Because it has velocity in the x direction, the kinetic energy reaches this value. At the peak height, the body will start falling down. So as the body starts falling down, it will start gaining velocity in the y direction, negative y direction. So now the kinetic energy is increasing again. At the same time, the potential energy will start to decrease until it reaches almost the same level. At the same level that it was fired from, it will have the same potential energy. At this exact time, the kinetic energy will reach its original value. So now I have the original position. At the original position, I have the same exact kinetic energy. But because the ground level is below the firing position, the body is going to continue gaining kinetic energy, while at the same time the potential energy is decreasing because it is going below the firing level, which was here. So as you can see, it will continue to lose potential energy, gaining kinetic energy, until suddenly it hits the ground. What will happen when it hits the ground? The potential energy does not change because it will remain at the same level. But what will it change is actually the kinetic energy. So if I zoom right here, you can see at this moment, at this exact moment, we hit the ground. Because we hit the ground, the kinetic energy reduced from this amount to this amount in no time. In one time step, we lose this amount of energy. So this amount of energy due to the impact will depend on the restitution coefficient. So what will happen next? We lost some energy. Because we lost some energy, the body is going to bounce back up until it reaches the maximum height. Because it's going up, it will gain potential energy and it will lose velocity in the y direction until it reaches the maximum height again. At the maximum height, it's going to have zero velocity in the y direction. But notice, the potential energy that the object is reaching here is much less than the potential energy right here. Because we already lost this amount of kinetic energy, this will be the same as what we lost right here. Again, the body is going to start falling down until it hits the ground again. See, here over here again the same process will repeat. In no time, the kinetic energy changes from this value to this value. Due to the impact, the body had lost some energy. Again, the body will bounce back and it didn't reach the maximum height as it before. Because we lost some energy, the peak potential energy here did not reach the maximum value. So this is what we have for the change in the potential energy. Before you lose your data, please save your model. Now again, it will be nice if we have an animation for this projectile while it is bouncing. So what I'm going to do, I'm going to add an animation to I'm going to create a new page, and in that new page I'm going to add animation with the motion in the X and Y direction. So how do I do this? I'm going to select a new page. When I click on this icon here, it's basically creating a new page. In this new page, I will split it into two parts. So this is our new page. I'm going to call this page animation. How do I change the name of the page? I can right click and override the name animation. Now this layout, I'm going to have side by side two plots side by side. So if you look under animation, you have one plot 5. I'm going to split this page into a side by side. So we'll go to this plot right here and select two plots side by side. In the right hand side, I'm going to create animation. How do I create animation here? I'm going to select this area first and then go to this drop down menu, click and select animation. Once we select animation, it will change the shape of our model. So what I'm going to do, we will go to overlay and select last run. So as you can see, this last run will load the model for us. So now we have the animation is displayed. Over here, I would like to plot our model. But what I would like to plot, I would like to plot the motion in the Y direction against the x direction. Oh, what do you mean? In those plots right here, you have the plot against time. Now I would like to change this. Instead of having the x-axis is the time, I would like to make the x-axis is actually the displacement in the x. How do I do this? I can go right down here and select the independent data, the independent axis data. By default, it's going to select the time. I would like to change this time, so I'm going to click on data. Once you click data, it will give you all the parameters and the characteristics in your system. You can filter them. So now I can select bodies. You can select the projectile. Then I'm going to select the center of mass position, the x-axis. This is the displacement of the center of mass in the x-axis direction. I'm going to use this as the x-axis for our plot right here. So again, in order to select this, we are going to select the independent axis. Instead of being time, I'm going to change it to data, and then filter by bodies, select our projectile body, the center of mass displacement. I will select the component in the x direction and click OK. Now as you can see here, this is what is used as the x-axis in our plot. Now what I want to do plot here is actually the y displacement, the altitude. So I'm going to select the characteristics, component y. Now I have the y selected against the x. I will select add curve. Now this is what you have. You have the displacement in the y direction against the displacement in the x direction. You can edit this plot as much as you want in order to make it look better. So I'm going to make this plot. I'm going to change the name of our y-axis as the name of the curve. Instead of y displacement, I'm going to just center of mass y, going to call it like this, center of mass y displacement. And as you can see, I can move this legend to the top right. So I'm going to select the legend from here, make it in the top right like this. So now I can see the curve. I don't need the analysis and I don't need the time and the date, so I'm going to hide those. So over here I'm going to look at plot, the analysis I don't need it, the date and the time stamp I'm going to delete it. So now you can see our length. This length I'm going to change it to make it travel, horizontal travel, and this length I'm going to make it vertical travel or altitude. So I'm going to select the horizontal x-axis. This is the name, length in millimeter. So I'm going to call this horizontal travel in millimeter. And then this, the y-axis, I will select the vertical axis, change the name and call it altitude, projectile altitude. Now if you would like to see the motion, you can click on this part of the window. You will see the animation controls. Now you can run the animation from here. So you can see the projectile is flying, falling down, hitting the ground, flying again, and so on. Now what I'm going to do, I'm going to record this into an AVI. So you can, in the animation here, as you can see, we have 200 frames. So when you generate the AVI, you will see 200 frames. If you change this increment, you can make it run faster. So instead of having 200 frames, I'm going to say make every 2 frames. So I will get only 100 frames. And this, I don't want it to loop. I will just make it to fly only once. Then I'm going to record. So now, as you can see, the animation is progressing. The projectile is flying. The crosshair is showing the position. You can see the X against Y. Also, you can see the progress of your animation right here. You can see the frame number generated right now, so you can monitor the progress of your AVI creation. So I'm going just to wait for this animation to finish, and then we can look at this AVI. Now the animation is done. I can go to my working directory. I should see my animation is created there. So this is my animation created just right now. I can double click and open this animation, or right click and select certain player if you wish, whatever player you would like to have. Remember also, this animation is going to be created in your working directory that you selected at the beginning. One more thing that I would like to cover today is how can we export certain amount of data from our model. For example, if you would like to use something like Excel to process your data. So here I'm going to show you the animation first before we go to exporting data. I'm going to select Windows Media Player. So as you can see, Windows Media Player is displaying our animation here. Nice animation. You can see the object is flying, while at the same time you can monitor the altitude against the displacement in the X direction. So assume I would like to send for example, the measure. We already have the data for the measure, and I would like to export the data for this measure. I can go to File and select Export. In this window, I would like to select Export. And as you can see, Adams is giving you variety of options that you can use to export. One of them is a spreadsheet or numeric data. For now, I'm going to look at numeric data because this is the simplest form of data that we can export right now. So I'm going to select numeric data. Now, Adams is going to ask you what file do you want to export. So it's asking you for the name of the data that will be saved to. I'm going just to give it test altitude, or let's say test data export. Data export. And I'm going to give it extension .text so that you can open it with any text editor. Now, what type of data do you want to export? So here we select the data that we will export. In order to select the data, you right click, and here you have the result set. So now you can browse. it's giving you everything that you have. So if we look at the beginning here, we have the time, you have the projectile, which is the part in our model. We have y displacement, which is actually the measure that we have. Also we have the displacement. So if we look at, I would like to get the time, and also I would like to get something from the y displacement. So you can expand the y displacement. Under the y displacement, you can see something called q and the time. Q is actually the data that this measure is storing, and the time is time. Also, I would like to export from from our projectile, I would like to export the y displacement. So the way we are going to select our data, I'm going to select the time, x displacement from the projectile, y displacement from the projectile, and the values that we have in the measure, q. In order to select multiple elements, you can use control key. So I selected the time, press and hold the control key, and then select the values that you would like to look at. You can select x and y and the q. If you would like also to see how the velocities in the x and y are changing, you can select them. There is no doubt about that. So you can select all of those values. So now I have 1, 2, 3, 4, 5, 6 elements. Now I can click OK. Those are the values that will appear in this order. You will have the time, velocity in x, velocity in y, the displacement in x, displacement in y, and the measure. The measure for our case right now is actually the same as y. We should see no difference between them. If I click OK, now the file should have been created. I can go back to our folder right here, and you see the file is created right here. This file, the same name that I specified, and as you can see, the size is not as large. Now I can open this file and edit it. So I can right click and select to look at the values that we have in this file. I have Notepad++ editor, so this is the editor that I'm using for my editing. And as you can see, right now it loaded the file for me. At the beginning of the file, you can see the channels. So we have A is the time, and then Vx, Vy, X, and Y. Those are the 5 columns that we have here. Now, if you would like to open this in Excel, you can open your Excel and import the file and choose the format that you are looking for. One thing that you need to notice is that the velocity in the x direction was constant. As you can see, the velocity in the value in the second column here are constant. They never change it. Also, you have the time is increasing from 0 until the time here, the end time. Also notice something here that happened that we didn't like. This file is limited with 5 columns. So what is our measure? Actually, Adams wrote it down here. At the end of the file, we have this measure, the values of our measure right here. which is almost the same as the values of y. So now assume you would like to open this file in Excel. I'm going to open an Excel sheet and then choose open. From file I can choose open and I can browse to our file. So our Excel file is saved here. Our data file is saved in our directory MA Spring 2020. Now I don't see it because it appears like Excel is looking for specific format. So I'm going to ask Excel to select text file. So now you can see test data export, and I will select open. Excel is not going to open it directly because it's not in the Excel format. So what we need to do is to tell Excel how this data are arranged. So you can select, instead of fixed width, you can select delimited. And then next, you can select the delimiter is space. So now you can see the file right here, and then select finish. Once you select finish, you see all the files, the columns appeared here, and again the measure is appearing at the end. So I'm going to cut this line and move it to the other side. So I'm going to cut this part of our measure data and move it to the end. And you should see this measure has the same information as the y displacement, exactly the same values. Now you can do the processing for your data in your Excel sheet. If you need to add charts or you need to add bar charts or anything, you can do that. You can also use it in MATLAB program if you would like to do a control or something like this. You can use this data